Hello everyone, welcome to topic 7.9 notes, Introduction to Le Chatelier's Principle. By the end of this, you should be able to identify the response of a system at equilibrium to an external stress using Le Chatelier's principle. Le Chatelier's principle states that a system at equilibrium will stay at equilibrium when a stress is applied. In other words, when a stress, such as change in temperature, pressure, or concentration, is applied to a system at equilibrium, the reaction will respond in order to minimize the effect of that stress. Recall that the equilibrium constant for any reaction at equilibrium is mathematically determined by dividing the concentrations of the products raised to their stoichiometric coefficients by the concentrations of the reactants raised to their stoichiometric coefficients. For the general reaction given below, the equilibrium constant would be written as follows. As long as the temperature remains unchanged, the value, making sure we understand the value of the equilibrium constant, will remain the same. The only thing that can change the value of K is temperature. Le Chatelier's principle is useful in determining how a reaction at equilibrium will react to a certain stress that is applied. For example, if some of the reactant A from the reaction above, the concentration of A is increased, this disturbs the equilibrium of the reaction because now you've got more A and it needs to fix it to get back to equilibrium. In order to reestablish the equilibrium, the reaction will shift to favor the reaction that uses up A. You have extra A now, so you're going to use it up. In this case, it is the forward reaction. Another way to look at it is that the addition of A would temporarily cause the value of Kc to decrease. This means that, and it's not Kc, it's technically, Q. So Q then becomes less than Kc, because you have more reactants than products compared to the equilibrium state. However, we know that Kc must remain constant, so the reaction shifts in a way to regain the same value. The reaction will react to decrease the concentrations of reactants and then increase the concentrations of products, so we say it shifts towards the products, or the forward reaction, the forward reaction is favored. If the concentration of products is increased, so then Q becomes greater than K, the reverse reaction would be favored, as that reaction would use up the added product. The value of Kc would temporarily increase, so Q is now bigger. So to reestablish the same ratio of products to reactants, the reaction will shift towards the reactants in order to alleviate the stress placed on that system. So as a reminder, Q, the value Q, the quotient, allows us to see where a reaction is with respect to equilibrium when we compare it to K. K is the ratio of reactants to products at equilibrium. Q lets us see where we are with respect to that equilibrium and how the reaction will shift. So by removing a reactant or product, or decreasing the concentration of one of the chemicals, will cause the opposite effect. So if you decrease or take something out, it's going to shift towards that. The reaction will shift to reform that missing or lower amount of the material. If we consider a gas phase equilibrium reaction, the equilibrium expression is written in terms of the partial pressure of the gases. So for example, we have this reaction where Kp is equal to the pressure of dinitrogen tetroxide divided by the pressure of nitrogen dioxide squared. When you are working with systems that involve gases, changes in pressure can cause a shift in the reaction. If the pressure on the side on the system is increased, the system will try to alleviate that stress by reducing pressure and shifting to the side with fewer moles of gas. In this case, that is the product side. How do we compare moles of gas? It is by their stoichiometric coefficients. So we would, for every gas on the product side, add the coefficients together, and that's the moles of gas for every mole of reaction. And you do the same for the reactant side. And in this case, the one with the fewest moles of gas, the product side, it will shift towards that when we increase pressure. If we increase the volume, it can also have an impact on the equilibrium. If you recall in the gas laws, increasing volume causes the pressure to decrease and vice versa. So if we increase pressure or decrease volume, it's going to shift towards fewer moles of gas. And remember, it's just gas. Liquids and solids and aqueous solutions don't count. And if we decrease pressure or increase volume, we're going to shift towards more moles of gas. Okay. So if the reaction 2NO2 yields N2O4 is at equilibrium and the volume of the container increases, as we were just discussing, the pressure would decrease. The system would counteract that by shifting towards the reactants because there's more moles of gas. Adding an inert gas to the reaction at equilibrium will have no effect because they remain at equivalent partial pressures. The partial pressures aren't changing, and the partial pressures are the gases' kind of way of denoting concentration, but in units of pressure. The final type of stress on a system at equilibrium is changing the temperature. In this exothermic reaction at delta H is negative. Heat is released in the reaction. If the reaction is heated, the reverse reaction then becomes favored, producing more reactants and consuming products. Increasing the temperature is similar to adding a product. In this case, it shifts the reaction to the left. Decreasing temperature of the system would cause the reaction to shift to the right in order to replace the energy that was removed. When this reaction is cooled, more products would be formed, thereby consuming the reactants. Okay, and as you remember, you're going to treat delta H as a reactant, and that's when it's endothermic, or product. That's when it's negative delta H based on its sign. Oh, I ran out of room. Sign. In general, heating or cooling a reaction will cause it to shift in the same manner as adding or removing a reactant or product. It depends on if the reaction is endothermic or exothermic. Heating will cause the reaction to shift away from heat in the reaction, and cooling would cause it to shift towards the heat in the reaction. Since the ratio of reactants to products is altered with changes in temperature, the value of K will change when a system is heated or cooled. The addition of a catalyst to a system at equilibrium does not cause stress to the equilibrium. Catalysts decrease both the forward and reverse activation energies. So since the Hill total is being decreased, adding a catalyst makes the reaction reach equilibrium faster. It does not change the position of equilibrium. Le Chatelier's principle allows us to predict the effect that any stress will have in different measurable properties. For example, we can predict changes the stress will have on the pH of a system that involves acids and bases, the temperature of a system that involves the absorption or release of heat, and color changes for systems where one or more reactants or products are colored, which we're going to do some of those coming up here soon in class. So, in an endothermic process, so endothermic is a key word here. This means that heat is a reactant. Okay, so we would have it on this side of the reaction. We're going to say, does it shift in the forward or reverse direction? So using Le Chatelier's principle, predict how the reaction will respond to each of the following stressors. So for this one, we're going to add more of this. That means that it is going to shift in the forward direction. So it shifts away from additions. Okay, so adding shifts away, removing, so we're going to remove some of that, is going to shift towards. So shift, we're going to move towards CO, so that is in the forward direction as well. Okay, and then we're going to increase the pressure. That means it's going to favor the side with fewer moles of gas, right? They're going to be more compact or tightly packed, and so it needs to get rid of some of the gas particles to maintain the partial pressures. Okay, so here we have 1 mole of gas because the coefficient's 1, and then we have 1 plus 1 is 2. So it's going to favor the reactant side, so it's going to shift in the reverse direction to reduce the pressure inside and reestablish equilibrium. Okay, then finally, removing or decreasing temperature. That's like removing or energy. So we're going to remove energy, and that's on the reactant side. So when we remove or decrease something, we're going to shift towards it. So we're going to shift in the reverse direction. Okay. So now we're going to look at the we do. If the reaction consider the reaction known as the Haber process given here. It is determined that increasing the temperature causes the equilibrium to shift towards the products. Does this mean that the reaction is endothermic or exothermic? Explain your choice. Please pause the video and try A now. Okay, so you should have gotten that this is an endothermic process, and this is because adding, so energy and adding energy shifts forward. Right, so that would give us, because if we put energy on this side, and adding more of this is going to cause it to shift that way. If the reaction is at equilibrium and pressure is increased, which direction will the equilibrium shift? Okay, so because these are all gases, we have to look at total gas count. So I have 1 mole from N2 plus 3 moles from H2, which is a total of 4 moles of gas on the reactant side. And then on the product side, we have 2. So if we increase pressure, we're going to shift to the side with fewer moles of gas, which means we're going to shift towards the products or shift in the forward direction. Because it's going to make more products and have fewer moles of gas. Okay, then we're going to do C. The Haber process is used to create ammonia as an industry standard. In order to create the largest amount of product possible, they allow the reaction to come to equilibrium and then cool the reaction quickly. Use your knowledge of intermolecular forces to explain why this is deemed the best way to proceed with the reaction. So one of the key things to pay attention to is that they're asking for you to cite intermolecular forces. Okay, so you're going to compare intermolecular forces of the 3 gases and determine why NH3 would be easier to remove from this, because you're going to want to keep creating product, which means you're going to need to remove it. So pause the video and try that now. Okay, so we should have seen that cooling quickly. causes the NH3 to condense and removes it from the system, because it goes from a gas to a liquid, and we don't look at liquids in an equilibrium system. And the reason for it, since we have to cite intermolecular forces, it condenses first due to strong hydrogen bonding between molecules. Okay, so using this information and these, you're going to practice with the you-do questions that follow. Check your work, and thank you for tuning in.